So in the last video, I defined something called a group. A group is a set G with an operation. I called it star, and it has associativity. It has an identity, and it has inverses. It may or may not be commutative, and I'll talk about that maybe later. But now I want to think of some examples. So there are two examples that we've sort of already talked about. One is the real numbers with the addition as the operation. Another one is the real numbers minus 0, and by minus I mean set difference. Real numbers minus 0 with the multiplication. Maybe I'll write multiplication as a dot. Sure, why not? The other thing I want to do is I don't want to write out our set difference 0. I'm going to put this x here, and that's going to mean elements of R that are not 0. And this is called, if you read it, it's called R cross. It's a common mathematical notation. And the nice thing about it is I don't have to write set difference 0 every single time. I can just write R cross with this little cross. The cross is supposed to be multiplication. It's not supposed to be an X. So what are some other examples? Well, another example of a group that works like with addition is the integers. So let's think about this. Associativity, well, real numbers are associative, right? Real numbers are associative, so therefore so are integers. The identity for plus in the real numbers was 0, and that's an integer, so we're good. We're good about that. And lastly, we are looking for inverses. That means that every integer has to have a negative integer that we can add to it, which, if you know what the integers are, is true. If negative 1 is an integer, you add it to 1, it's 0. Negative 57 or positive 57 or 63, each of them has an inverse which you add to it and you get 0. A non-example would be the natural numbers. Natural numbers are associative, and depending on whether you believe that the natural numbers have 0 in them or not, it might have an identity element, but it does not have inverses. There are no negative numbers in the natural numbers. So natural numbers are not an example of a group. Let's see. What is an example of a group that uses something like multiplication? Okay, well, I can talk about the rational numbers. Also with the multiplication, I'm putting the cross, the Q cross here. You say this as cross, not as an X, to show that I don't want 0 in there because 0 would violate the inverses axiom, but without 0, it's just fine. Pi is no longer in here, or any other irrational number, but for every number that I do have, like for example 2/5, I have something that I can multiply it by, which gets me 1, 5/2. A non-example for multiplication is the integers. They were a group under addition. They're not a group. Maybe I can say z multiplication. I can say z cross if I want to. None of these will be a group because if I have, say, I mean, it fails very quickly. If I have two, if I think about 2, I want to multiply something by 2 and get 1. Well, there's only one thing that could really be. It's 1/2. And 1/2 is not an integer. So there's, and for any number that's not 1 or -1, you can do that for z. Other examples of groups, maybe I should put down, for those of you who've seen linear algebra, it's sort of related to this one with the real numbers, but if I have Rn with plus, that's also a group. That's also, and it's just addition. It just sort of works the same way. And so, okay, now that we've talked about these examples, maybe I want to make one more definition. So that definition, something you've noticed about all of the examples that we've talked about so far, is that they are indeed commutative. So it turns out there are some very interesting groups that are not commutative, and that's one of the things that we're going to start to study next. But the things that are commutative have a special name. So if a group is commutative, then it's called an Abelian group. Abelian, even though I haven't capitalized it, actually comes from someone's name. Mathematician is Abel. He was well known for proving that there is no general quintic formula. So there's the quadratic formula, and there's actually quintic formula. There's a quadratic formula, and there's actually a formula for cubics, for third degree polynomials quartics, if you've seen that. But there is none for quintics, and Abel was the one who proved this. There's also something called the Abel Prize. It's given away for mathematicians who have made a lifetime contribution to mathematics, and it's the same Abel in Abelian. So some interesting maybe things about Abel there. But all of the examples here, well, I mean, this isn't a group, so maybe I shouldn't say this guy or this guy. But all of these guys are Abelian.